Right, so 8.1 theories of acids and bases. Quite a lot to get through in this section. So this is what we'll be looking at for the first part. I think there's about 8.1, 2, 3, 4 and 5. This is 8.1. And it's all about Bronsted-Lowry theory. So Bronsted-Lowry theory is probably how you've always pictured acids and bases, and it's all about protons, right? So this H plus is a proton, and so acids are proton donors, bases are proton acceptors, and you can see here a couple of examples where the HCl is donating a proton, and therefore that's acting as a Bronsted-Lowry acid. And here you can see water accepting a proton. Oh, sorry, so the water in this example here is donating a proton to the ammonia. And again, the water there is the Bronsted-Lowry acid. The NH3 is the Bronsted-Lowry base. Now, when something gains or loses a proton, we can often think of this idea of conjugate pairs. Now, conjugate pairs, as a quick check, they've got to differ by an H+. Right? That's the key thing. So your conjugate pairs differ by H+. So you can see here we've got HCl and what should really be Cl minus. So when we gain or lose an H+, that's the difference that we see. Gain or lose an H+, gain or lose an H+. These are conjugate pairs. So this, gaining an H+ that way, losing an H+ that way. And it also means that when we look at reactions, we can very often partner up substances. So here, NH3 plus water, as we saw in the last example, this is going to be acting as a base. Right? It's accepting an H+. And its conjugate partner is that one. Conversely, if we were to go the other way, when this loses an H+, it's acting as an acid. So we can call this base one, acid one, that's one pair. And this is the other conjugate pair there. Two definitions just to be aware of. Amphiprotic and amphoteric. So amphiprotic is all about H+. So they can act as a Bronsted-Lowry acid and base. In other words, they can gain or lose the H+. So there's a big focus on H+ here. Amphoteric, a little bit broader term, in that the substance is able to show both acid and base behavior. So you maybe remember back to periodicity, we're looking at aluminium oxide. It can react with sulfuric acid, which means it's acting as a base, or it can react with sodium hydroxide, which means it's acting as an acid. And we describe that as amphoteric. We wouldn't describe it as amphiprotic because there's no H pluses here, according to that definition. So those of you doing higher level will learn a little bit about the Lewis theory, and you'll see that that's all about electron pairs, and so we'll see more to do with amphotericity there perhaps than amphiprotic substances. Right, 8.2, properties. This is what we need to get through. Some basic reactions of the acids, and you can see them listed here. So very important from a chemistry perspective that you're familiar with these reactions and can almost sort of recognize, oh, I've got an acid plus a metal. You can then predict what the products are going to be. So acid plus metal goes to salt and hydrogen. There's an example there. You see some examples of some common acids listed there. And the salt is simply a substance where your H, your proton in your acid, has been replaced by a metal. So if I'm starting with sulfuric acid, I'm going to end up with a sulfate. If I start with nitric acid, I end up with a nitrate. Hydrochloric acid gives me a chloride. Phosphoric acid is going to give me a phosphate. Ethanoic acid, a little bit more obscure, gives me an ethanoate. Sodium ethanoate is the name of that substance. Other things to check through on here, alkalis, these are just soluble bases, and whenever we undergo a neutralization reaction, it is exothermic. All right, it's exothermic. So these are reactions of acids and bases that you should be familiar with. Reminder about those salts. So we're replacing the H with a metal, and you can see the type of salt that we're going to produce as a result of that reaction that it undergoes. So you can name the compounds produced. You also maybe need to think back to your work on moles, quantitative chemistry. When you work with some solutions there, you probably did some titrations. This page is a recap on how to kind of read your burette, what data you should be recording, and then making sure you're working through as carefully as possible to get what we call concordant titers, ones that are very close to one another. And on here you can see a worked example of how to process the data from a reaction. So again, it's the same kind of 3 steps we did in the quantitative stuff. Convert what you've got to moles, look at mole ratios, and then come out of moles. So you can maybe pause this and have a look at that calculation there. Skipping a little bit to 8.4, we need to know the difference between strong and weak acids and bases. So that's what we're going to look at. And essentially the big difference between strong and weak is a strong substance undergoes complete dissociation. Complete dissociation. And a weak one only undergoes partial dissociation. And you can maybe see the differences. You've got these equilibrium signs here. So only some of this acid is ionizing like this. Only some of this base is reacting with the water, very small amount. So that means in terms of detecting which is which, because this undergoes complete ionization, every single molecule of HCl, a strong acid, or every single NaOH, a strong base, will give you ions. Because that means you've got many, many more ions. It means you've got much better conductivity. Right? More ions, better conductivity. If you've got more of these H pluses, and maybe you do over here, so H3O plus and H plus are kind of synonymous. If you've got more of these H pluses, it means you're going to have a much lower pH, right? A lower value of the pH, or conversely here a much higher value of pH. And you tend to see when these acids or alkalis react a faster rate of reaction. Now you don't necessarily, well in fact you don't get any more product. The number of moles is still important, but you get a faster reaction because the concentration here is greater. Now why do you end up with the same number of moles? Well, as some of this stuff reacts away, the equilibrium gets dragged across to replace it. So you're still going to eventually be using up all of your acid. It's just the initial concentrations are less, which means that the rate of reaction is a bit slower. In your data booklet, you will find several examples of weak acids. Right? You can refer to those and look at their names. pKa will be something that's more important when we do some calculations based on acid chemistry. So this is just going back. We've already talked about conjugate pairs, conjugate partners. If you've got something that is a strong acid, then its partner is going to be a relatively weak base. Okay, and conversely, if you've got that strong base, then its partner is going to be a weak acid. So if we look at these, HCl, strong acid, this really isn't very good at picking up protons. It's not a very good base. However, here, ethanoic acid, which is a weak acid, will mean that this substance here does have some basic properties. So if we were to add some water to that, we would find that it would maybe pick up one of those protons and give us this. And so that means if we actually have a solution of this stuff, which would maybe be sodium ethanoate, so we've got an Na plus in there as well, if we have a solution of that, we would find that that would have a pH greater than 7 because it's releasing these OH minus ions. So depending on what you start with will affect the relative strength of its partner. Again, you can see another example there. This is a weak base, which means that this has some acidic properties. So this can go and do this, which releases H plus ions, and as a result we'd end up with a slightly acidic solution. And so if we start talking about what these substances could actually be rather than just the ions, we've got that, oops, sorry, and we've got NH4Cl. Those are kind of two salts when we hydrolyze the salts by putting in the water, we're finding these unusual pHs. We call that salt hydrolysis. Right, going back, 8.3 pH scale, probably something you're familiar with. I'm going to take it a little bit further. This is what we're going to cover here. But key point is that it's a measure of the H+ ion concentration. That's what it's measured. We can, in the labs, we can use our pH meters, get a more accurate value, maybe more precise, I should say. Or we can use a universal indicator. See those color changes. Big thing about it is that it's a logarithmic scale. So 1 unit equates to a 10-fold change in H+ ion concentration. And at 25 degrees Celsius, as those of you doing HL will find out, that is pH 7. Below this we call things acidic, above it we call things alkaline. So if milk has a pH of 6 and baking soda has a pH of 9, what can be deduced about their relative H+ ion concentrations? Oops. Well, we can look at how many pH units we're skipping. So we're going from 6 to 7, 7 to 8, and then 8 to 9. So we've got 1, 2, 3 units. So it's 10 times 10 times 10, which is 1,000. Right? So there is 1,000-fold difference in H+ ion concentration between milk and baking soda. And because the milk is the lower value, we could say that milk is 1,000 times greater concentration of H+ ions than the baking soda. Right. So this is what makes it that 10-fold change. pHp is kind of just meaning minus log 10 of what follows. So that's what the P refers to when you see that. So it's minus log 10 of the concentration of H+ ions. And if you're a little bit interested in this, you can see that we're dealing with water primarily, just as a starting point. So water will dissociate to a very, very small degree, which means that we can write an equilibrium constant, right, because it's an equilibrium. Now we assume that because the water is so massively in excess, its concentration isn't really going to change very much, and we can redefine a new equilibrium constant, Kw, as that. Right? And again, if we wanted to call something pKw, we could put a P in front and it would look like that. So Kw refers to the dissociation of water. Kw is the ionic product of water. And pKw, you can see there by putting a P in front, we get this term produced. Right, here's some examples using the equations on the other page. And the reason that we're introducing pKw there and Kw was because it was a way for us to link between H+ and OH- ion concentrations. So maybe if we start with this one over here, calculate the pH of a 0.02 molar solution of HCl. So we see HCl is a strong acid, complete dissociation, so every single molecule of HCl is going to give us a molecule of H+ and one of Cl-. So that means the concentration of my H+ ions is also going to be 0.02. So then I can just put it in my equation and I can solve it for pH. Now, coming over here, then calculate the concentration of solution of barium hydroxide with pH 12 at 298 Kelvin. Right, so the pH again refers to the concentration of H+ ions. So, oops, there's our concentration of H+ ions based on that. Now, assuming we're working at 25 degrees Celsius, we've got this relationship, Kw, that links H+ and OH-. So I know that Kw is 1 times 10 to the minus 14, and substituting this value into there means that I can work at my OH- ion concentration. Now I have to be a little bit careful because barium hydroxide gives me twice as many OH- because it's got 2 OH- in there. So that's why I've got this dividing by 2 factor, and that gives me the final concentration. And the last one here, again, says they're not required at standard level. You can have a look through it, but it's interesting to note that, because water, when it dissociates to equilibrium, we know that Kw values are affected by temperature, or equilibrium constants, I should say, are affected by temperature. Then we find that at that higher temperature, because my equilibrium is going to be further to the right, it means my concentration of H plus ions is greater, and it means that my pH is no longer what we used to consider neutral. Right, the pH is at 5.5, not 7. The water is still neutral because I still have the same numbers of H pluses and OH minuses. Right, so it's not like you're going to put your fingers in and find that it's corrosive. Because I've still got the same numbers of H pluses and OH minus ions, it's still neutral, but I do have a different value there, which means that my pH is different again. Right, last section, acid deposition. A few things here that we have to be familiar with in terms of sulfur oxides and nitrogen oxides. So acid rain, so pH below 5 or 5.6. See, that should read 5. So acid rain has a pH below 5. Oops, I see. We can use the term acid deposition to include things that maybe you already think of, like rain, snow, mist. So that's wet deposition. Dry deposition is where this stuff falls as dust or smoke, later giving an acidic effect. So sulfur oxides, where they're coming from? Well, sulfur is often attached to coal and oil. When you burn those fossil fuels, the sulfur gets burnt as well. And you can see here the process by which a non-metal oxides gives us an acidic substance at the end once it's reacted with dissolved in the water. Nitrogen oxides, where do they come from? Well, there's lots of nitrogen in the air. We've got our internal combustion engine, very, very hot, which means some of our relatively inert nitrogen can combine with oxygen to give us nitrogen oxides. And again, you can follow that through and you can see my non-metal oxide giving me an acidic solution of nitric acid at the end. So there's a little picture that I found that summarizes everything that's going on in terms of dry deposition and wet deposition. What are the effects? Well, again, you can pause this and read through it at your leisure, but you need to know about the effects on materials, particularly statues. That's probably something that you've seen around. We're going to see oxidation of metals. For aluminium, whilst itself is a reactive metal, because it's coated in this layer of aluminium oxide, it doesn't corrode very much at all. But if we remove that, then we're going to see the cars or whatever starting to react with those acidic substances. Plants has an impact on them. Water, we've got this idea of releasing aluminium ions from rocks, which is harmful to the fish. It's also a cause of eutrophication. And then there are some health effects for humans as well. So what can we do? Well, we can try and remove the sulfur before we combust it. Okay, so there's two pre-combustion methods. Or we can try and trap the sulfur dioxide once we've burnt the fuels before it gets released into the atmosphere. Right, and again, you can see there a method to do it using calcium oxide. What about the nitrogen oxides? Well, catalytic converters are now commonplace in cars, and they're undergoing this transformation, helping the nitrogen oxide react with another harmful gas, carbon monoxide, to form less harmful products. And we can also look at making the temperature of the combustion lower so that we get less of that nitrogen oxide in the first place. Other things, well, use less fossil fuels, use more public transport, and fixing ecosystems. It's difficult, but you can, for example, chuck lots of lime into lakes to reduce the levels of acidity within them. Great.